The generator effect is a fundamental principle of electromagnetism that explains how a potential difference, or voltage, is induced in a conductor when it moves through a magnetic field. This phenomenon occurs because the movement of the conductor causes it to cut through the magnetic field lines, which disturbs the magnetic environment around the conductor and generates an electromotive force, EMF, within it. When a conductor, such as a wire, moves through a magnetic field, the magnetic field lines are cut by the conductor. This cutting of field lines induces a potential difference across the ends of the conductor. If the conductor is part of a closed circuit, this potential difference drives a current through the circuit, creating what is known as an induced current. The direction of the induced current is determined by the direction in which the conductor moves relative to the magnetic field, as well as the orientation of the magnetic field itself. The induced current can be predicted using Fleming's right-hand rule. If the thumb of your right hand points in the direction of the motion of the conductor, and your first finger points in the direction of the magnetic field, your second finger will point in the direction of the induced current. One important aspect of the generator effect is that the induced current always opposes the change that caused it. This is a consequence of Lenz's law, which states that the direction of the induced EMF and the resulting current will always be such that it opposes the motion or change in the magnetic field that produced it. For example, if a conductor is moved through a magnetic field, the induced current will create its own magnetic field that opposes the motion of the conductor. This opposing force means that work must be done to move the conductor through the magnetic field, and this work is what generates the electrical energy in the circuit. The size of the induced potential difference, and consequently the induced current, can be changed by several factors. One way to increase the induced potential difference is by increasing the speed at which the conductor moves through the magnetic field. The faster the conductor cuts through the field lines, the greater the rate of change of the magnetic environment, and the larger the induced EMF. Another way to increase the induced potential difference is by using a stronger magnetic field. A stronger magnetic field has more densely packed field lines, so cutting through it induces a greater potential difference. The number of turns in the wire or coil also affects the induced potential difference. In a coil of wire, each turn of the wire experiences its own induced EMF, and these EMFs add together. Therefore, a coil with more turns will have a larger total induced potential difference than a coil with fewer turns, assuming all other factors remain the same. In practical applications, the generator effect is harnessed in devices such as electrical generators and dynamos. In a generator, a coil of wire is rotated within a magnetic field. As the coil spins, it continuously cuts through the magnetic field lines, inducing a potential difference and generating an alternating current, AC, in the circuit. This principle is used to convert mechanical energy, such as the rotation of a turbine, into electrical energy that can be used to power homes and industries. In summary, the generator effect describes how a potential difference is induced in a conductor when it cuts through magnetic field lines, and this induced current always opposes the change that caused it, in accordance with Lenz's law. The size of the induced potential difference can be influenced by factors such as the speed of motion, the strength of the magnetic field, and the number of turns in the coil, all of which play a crucial role in the efficient generation of electrical energy in various technologies.